Yeah, very good morning. Am I audible?
Yes, sir.
Okay, screen is visible.
Yes, sir.
Okay. Okay. So the last class we have done the Fourier series part. Okay. However, we have already done this during the last semester. That Fourier series, including its continuous version, like Fourier integral. Okay, and so I have already shared the link of that lecture, so you may go through it. So already completed, so I don't want to waste my time for that. So if you have any doubt, we can discuss it in the during tutorial session. Okay. Okay. So we can start with this second order linear PDEs. So while solving them, we will see that Fourier series method. Then also we will see the Fourier transform and its application to in solving PDEs, like we have seen for the Laplace transform case and Laplace transform versus ODE. Of course, you can also use Laplace transform for solving PDEs as well. Okay, right. So we'll see if time allows, we'll see the Laplace transform application as well. But our main concern is to use here Fourier transform. There are certain reason about it, so we'll discuss it later. Okay? Right. So the first point is about the second order linear PDEs. You have seen heat equation, wave equation, Laplace equation somewhere back in your the classes regarding the partial derivative, right? Okay. So we will pick up one of the application. We'll see how this vibrating string can be modeled into a real equation under some mathematical assumptions. Okay. Okay. Right. So let's wait for that part. Then if time allows, your TA will also discuss regarding the heat equation, maybe in in terms of modeling part when you are doing a tutorial. So then you'll may realize how how these PDs are related with the real life problems. Okay. Of course, some mathematical assumptions are required, right? So that we will discuss. Okay. Now, this the very first concept, similar for like first order PDEs. We have seen if you have one arbitrary function involved, that will correspond to the first order PDEs. You have two arbitrary functions, so that will correspond to second order PDEs, and the process will be the same. So what you do is here you have this equation for which you want to or equation, or you can say family, for which you want to find the corresponding PD here, partial differential equation, where f and g are arbitrary functions, u and v are functions of x, u, v, and w. All three are functions of x by x and y. So they are known functions. Okay, f and g are arbitrary, but u, v, w are known function in advance. Okay. So to proceed to find the PD corresponding to it, you have to proceed in the similar manner like in the first order PDs. So if I recall some of the line here, so you are Z equals to F of U plus G of V plus W. Okay, so you have to differentiate partially with respect to X, partially with respect to Y, partially with respect to means you have to find all the first order and second order partial derivatives and then try to eliminate this arbitrary function. So okay, so if you differentiate partially with respect to X, so Zx that is we have denoted by P is equals to, you know, right, F dash of U Ux plus G dash of V Vx plus Wx. Okay, now this if you differentiate partially with respect to Y, you have Q equals to F dash of U Uy plus G dash of V Vy plus Wy. Right now you have then again you differentiate partially with respect to X, so you differentiate this again with respect to X. Okay, so what you will get is which we are denoting by R, that is Zxx. Okay, so that's going to be now you have this is going to be, you have to use the product rule here. So F dash of U Uxx plus F dash of U Ux whole square. Similarly here here is F double dash. So G dash of V Vxx plus G double dash of V Vx whole square plus Wxx and so on. Okay, similarly S, what is S is Zxy. It's a notation. That's going to be, means you differentiate either this or this. We are assuming that everything is fine, mixed derivative theorem is applicable, okay, and so on. Those things we are already pre-assumed. Okay, so here I'm just differentiating this partially with respect to Y. So you have F dash of U Uxy plus F double dash of U Ux into Uy plus you have similarly G dash of V Vxy plus G double dash of V Ex into Vy plus Wxy. Okay, so now similarly you have the fifth equation, so you will have the five equations. Okay, T, that is Zyy, and I think with the symmetric argument you can also write this. Okay, or you can differentiate this. So you have this is going to be F dash of U Uyy plus F double dash of U Uy whole square Z double dash of V Vy whole square plus G dash of V Vyy plus Wy. So you have five equation in four unknowns. Okay, F dash, G dash, F double dash, and G double dash. So four unknown means like arbitrary functions, and you are interested in non-trivial solution, obviously. So you will see the coefficient matrix should not be invertible. Okay, so you arrange all the coefficients, what you will get is the following. So I'm just now directly jumping to the final case. Okay, so so we obtained a five equation in F dash, G dash, F double dash, and G double dash. And so on eliminating the arbitrary quantities, you have So this is first equation, right? Ux f dash of, so this is a coefficient of f dash. This is a coefficient of g dash. This is a coefficient of f double dash. This is a coefficient of g double dash in the first equation. Say first equation, second equation, third equation, fourth equation, fifth equation. Okay, so this is 5 equation. Okay, so you are multiplying it by, you have this is, I can say here the vector in coefficient matrix. The vector is you have, this is 1 f dash f g dash f double dash g double dash. So this is the vector, unknown vector through which you are multiplying. Okay, right? So that you can verify. So now what you require is the, you no need to, you are interested in a non-trivial solution. So that's why this coefficient matrix determinant should be 0. So now once you substitute this equal to 0, so this will lead to, so if you, this is 1 2 3 4 5 5 cross 5 matrix. Of course, you know how to identify the determinant of this. Okay, of course this involves 2 zeros here, so it's perfectly fine to go with the first row. Okay, and you have, you know how to proceed. Okay, now on solving this, what you will get is, you are going to get equation PD. Okay, so say going to be equation in terms of P, Q, R, S, and T. Okay, and rest of the things are known: Ux, Vx, Wx, Uy, Wy, Uxx, and so on. These things are completely, you are aware about it. Okay, so if I write in the general form, what you are going to get is the following. So again, we have denoted capital R as a coefficient of small r, capital S is a coefficient of small s, T, capital T is a small, it's a coefficient of small t, and so on. So that, okay, so you just accept them as a notations. Okay, R, S, T, P, Q, what, and W. We can, what we can say about it is they are going to be functions of x and y, non-functions of x and y. Okay, they will not involve z, so that should, that must be clear. Okay, and moreover means, like, you are going to get a linear PD. Okay, not a non-linear one, and you are very now much aware how to decide whether it is linear or non-linear. So product of derivative should not be there. Derivatives, power of the each derivative, whatever is, whichever is increasing, whichever is occurring. Okay, second order linear PDs R, S, and T. Okay, they should not be having the power is more than 1. They should be equal to 1. Okay, no transcendental function of R, S, and T, and so on. Okay, right. So this is a arbitrary one. So you can decide with this following. So you are here is U is known and V is known. Okay, so this you can take as an exercise. Okay, so here U is known to you, x plus ay. Okay, V is known to you, x minus ay. So from here you can find ux is 1, vx is 1, uy is a, vy is minus a, and you know uxx is 0, vxx is 0, uyy is 0, vyy is 0, uxy is also 0. So you have all the information and you can substitute here. W is also there, 0. Okay, so there is the W is a 0, right? Here is no addition here, plus W. So W is a 0 function. So Wx, Wi, and so on, all its derivatives are 0. So you can fix this row is, this column is completely PQRST. Okay, Ux, Vx 0, 0, Vy, Uy, Vy 0, 0. All these terms are 0. Not this term. So this bracket is going to be 0. Okay, so these terms can be replaced and you have a 5 cross 5 matrix determinant which you can solve. Okay, or you just ask, you will get it simply while doing the evaluation. It's like while you are differentiating 2 times, you will see the relation between uyy and uxx, sorry, zxx and zyy. Okay, so that is easy to follow. Either way, you can do this directly, okay, or you can jump to that determinant. Okay, and it's very straightforward. Okay, it's very straightforward. I think I can finish it in a line, in a 2 lines. Z equals to f of x plus ay plus g of x minus ay. So if you differentiate partially with respect to y, you have a time f dash plus not plus minus a time g dash x minus ay x plus ay, and again differentiate with respect to y, so that's going to be a square f double dash x plus ay, and you have plus a square g double dash x minus ay. Now if you differentiate this partially with respect to x, it's straightforward. F dash of x plus ay, chain rule, plus g dash of x minus ay, and you have zxx is going to be f double dash x plus ay plus g double dash of x minus ay, and now you can relate this zyy equals to a square times zxx. Okay, so you are obtaining the second order linear PD. Okay, so now if you have any doubt, you can ask. Yes, if there is any doubt, you can ask. Okay, right. So let's proceed. Okay, so similarly, if you have the following, here is, I think, this notation I here. Okay, if you have the sum of n arbitrary functions where vi's are known, okay, fi are arbitrary and vi are known, and we will get a linear PD of nth order. Okay, right. So that you can verify again. Okay, so let's consider a vibrating string problem. Okay, so okay, so let's consider a tightly stressed elastic string, the ends of which are fixed on the x-axis at x equals to 0 and at x equals to L. So you have a x-axis here and you have a y-axis, x equals to 0 and let's say x equals to L. So let's have a tightly stressed elastic string. Okay, so it will be very close to on the x-axis. Okay, right. Now what you do is, okay, let means like at t equals to 0, at t equals to 0, okay, you stretch it. Okay, means you have, let's say you have the, this is a initial position at t equals to 0, you, this curve is given by, let's say, not let's not down, let's say up. Okay, so let's take this curve is f of x at t equals to 0, this initial position is f of x, and you leave it. Okay, you stretch it at time equals to 0, the initial position you can find out. Okay, you can note it down, this is the initial position. Okay, and that you denote it by f of x, and then you leave it with the velocity, let's say g. Okay, the velocity of g of x. Okay, at every point x, so there will be different velocity. So then we will have the certain, so then it will start vibrating. So there may be a deflection, there may be maybe rotating or whatever. So what we are going to make some certain mathematical assumptions certainly here. So with velocity t equals to 0, at t equals to 0, you are stretching with this initial position f of x, and you are leaving with the velocity g of x. Okay, so if you denote, let's say I will denote this u of this by x, u of x comma t by the to the vibration of the string. Okay, so what it is given is means this is the vibration of the string at any point x and at any time t greater than 0. Okay, at any point x and at any time t greater than 0. So what is given is it initially you are having the position is f of x, and you are living with the velocity with, okay, velocity means rate of change with respect to time, right? So dou u by dou t at x comma 0 is given by g of, okay, and where x is lying, x is from 0 to L. Okay, x is lying to 0. So this is given to you, and you are interested in finding the solution of this problem. Okay, and so that you will able to have, I mean, at let's say a time 3 seconds, or what will be the position of this vibration at some like x at L by 2, okay, or L by 4, and so on. Okay, so that is your interest now. Okay, so we will have certainly have some mathematical assumptions, certainly like this the mass of the string is constant, okay, everywhere. Okay, so let's denote it by rho. Okay, the mass of the string is constant. It's constant, and also we are making the assumption is fully elastic, and it offers no resistance to bend. Okay, so it's fully elastic and no resistance to bend. Okay, now further, when you are fastening it, okay, this string, if you are going to stretch it and fastening it at the end, this x equals to 0 and x equals to, there must be there will be some tensions. Okay, there will be tension. Okay, so we will make the assumption that this tension is so large that gravitational force can be neglected. So which we see whenever you are dropping something from the height, so due to the gravitational force it goes down. Okay, so here gravitational force is not applicable. Okay, so that's so the tension is so like, okay, right. Then we will start. So let's see what are the more assumptions. Okay, so this is so when you leave with initial velocity, that string will certainly vibrate. Okay, and the problem is to determine the vibration of the string at any point x and at any time t greater than 0. Okay, so we make the following assumptions. The mass of the string is constant, say let's say rho. Further, the string is perfectly elastic and does not offer any resistance to bend. Okay, right. Now, the tension caused by stretching the string before passing it at the end is so large that the action of the gravitational force on the string can be neglected. Okay. Right. Now, the string performs small transverse motions in a vertical plane. Okay. So that is every particle of the string moves strictly vertically. Okay, so this is a mathematical assumption right here. So when you are, this is going to be vibrate. Okay, this is going to be vibrate. Okay, so it's the there is means the string is does not offer any resistance to bend. Further, it's going to be assumed that it's vibrating in a vertical plane. Okay, in a vertical plane means it's up and down. okay, there is a very deflection or deviation is very small. Okay, means a very little. Okay? It's small in absolute value. Means can be negligible, you can say. Okay, and the slope at any point, if you look at the slope, okay, it's going to be small, means near to zero. Okay, it's like means like you have a guitar. Okay, so if you just vibrate the string, it is you may not be able to determine the slope will not have large value. It's very small value when you make it if you tie it up, if you consider it as an x-axis. Okay, so it is working in the same direction. Okay, right. So now to model it now further, so let's take 2 points on the string which we denoted by p and q. So let's take p is at point x, and this is q is far apart with a distance is delta x. So let this x to x plus delta x. Okay, now means let's take t1 and t2 are the tensions at these points. Okay, and they are making the angle alpha with the horizontal axis. Okay, so alpha with here, and here is beta. Now see, as told, that deflection in the slope at every point is going to be small in absolute value. Means this, if you take the horizontal component, okay, these horizontal component, they will remain constant. Okay, so what are the horizontal components? Are nothing but t1 cos alpha and t2 cos beta. They are going to be the horizontal component. So they are going to be constant, and that you can denote it by t. Okay, that's going to be constant, and thus you can denote it by t. Now, vertical components are, what are the vertical components? Since this t1 is the negative direction, so one vertical component is t1 sine alpha, and another vertical component on at q, okay, is going to be t2 sine beta. Now, Newton's second law says that the total force is going to be, so what is the total force? Is t2 sine beta minus t1 sine alpha, force acting, is going to be mass into acceleration, right? So the what is the mass in this length of this interval is rho time delta x, and acceleration is dou square u by dou t. So this you will obtain by using Newton's second law. Now means further mathematics will be done here. So now you further divide both sides by t2 sine beta minus t1 sine alpha. You divide it by capital T is equals to rho delta x by capital T dou square u by dou t square. Now you just now what is t? T is t1 cos beta as well as sorry, t1 cos alpha as well as t2 sine beta. Okay, so use that fact. So what you will observe is going to be, so if you replace here t by t2 cos beta, and here you can replace it by t1 sine t1 cos alpha, because both are the same value, both has the same value. So t1 will get cancelled, t2 will get cancelled. So what you will observe is tangent beta minus tangent alpha is equals to rho time delta x by capital T dou square u by dou t. Now, what is tangent beta and tangent alpha? Is a slope, right? So it's going to be dou u by dou x and beta at x plus delta x. So beta is the angle made at the q point minus dou u by dou x tan alpha at the point P is going to be x. Now what I will do is I will just send this delta x on the left side. This is equals to rho by t dou square u by dou t square. Now if you see it carefully, I'm just writing in the further in the notation. Maybe you will look at it: x plus delta x comma t minus ux at x comma t divided by delta x is equals to rho by t utt. Now letting so because you have chosen q and p apart with delta x, let's p is going closer to q or q is going closer to p, okay, and means you have delta x is tending to 0. So letting this delta x is tending to 0, so this will imply the left hand side will tends to uxx at x comma t is equals to rho by t utt, which is nothing but the wave equation. So now this is going to be utt is equals to c square uxx, which you are going to denote c square is going to be positive always, okay. So c square is going to be t by rho. You know, t is the tension, okay, rho is the mass, okay. So this is going to give you, so this vibrating string is modeled into the wave equation, okay. So the vibration of the string is nothing but the solution of this wave equation, okay. Now with the initial boundary value, you can make it so this is the initial boundary value problem. So utt equals to c square uxx with initial condition is ux comma 0 is f of x and ut at x comma 0 is g of x, initially velocity. Now you can also make the Dirichlet conditions, means Dirichlet homogeneous conditions. Those are known as, means like at the end points there is no vibration, okay. At 0 comma t is equals to 0 equals to u at l comma t, where you are tying, okay, those points at x equals to 0 and at x equals to l, there is a homogeneous condition. These are known as homogeneous condition or Dirichlet condition. Okay, so this is known as initial boundary value problem for second order PD, which we will solve by using Fourier series method. Okay, or variable, in other words, variable separable method, and then it will lead to the Fourier series solution. Okay, so if you have any doubt, you can ask.
Hello, hello.
Yes.
Sir, have we got the UXX doing the letting delta x tending to 0? Like, have we formed that equation?
Yeah.
Yes, sir.
So what is the fundamental definition of a first derivative? Let's take partial derivatives. If you recall those classes, I think you will be able to get it. If you recall, let's take the partial derivative of, let's say, u of x comma t. I want to have ux, okay, at let's okay, ux, okay, at x comma t, partial derivative at this point. So what is the definition is fundamental limit delta x tends to 0, u of x plus delta x comma t minus u at x comma t divided by delta x. Are you aware about it?
Yes, sir. Yeah, sir, I got it. Okay. Like,
Okay.
we took limit tends to delta x into 0. Okay.
So similarly, if you have uxx here, so you are performing on ux now, right? Ux, then further
So
you are
we get
differentiating partially.
UXS.
Okay, yes, no,
Okay.
this will apply. Okay. Okay, right.
Yes, sir.
Any other question? Okay. Right. So let's move to the this. Okay, so let's we have done this. Okay. Okay. So we seek the solution of the following. This is one-dimensional wave equation. So if you increase here one more additionally plus let's say dou square u by dou y square, that will go to the second two-dimensional, and you can increase as many dimensions as you wish based on the problem. Okay, right. So now we are seeking the solution of the following one-dimensional wave equation under some additional conditions. So boundary conditions are is at the point at x equals to 0 and at x equals to L, there is no vibration at any time. Okay, and initial conditions are already explained to you. Okay, right. So initial boundary value problem. So we are going to use a variable separable method sometime, and it's also known as Fourier series solution. Okay, right. So whatever I am going to follow here in the variable separable method concept, the similar thing will be applicable in terms of, I mean, for the case when you are dealing with the heat equation. Okay. Similarly, for Laplace equation as well, you have to deal in the similar fashion. So there may be a separate type of solution that you will find. Okay. So that we will try to figure it out if some important thing you need to address there. Otherwise, you have to follow the similar solution solving method. Okay. Okay. So as the name is suggesting you variable separable means you are pre-assuming that the solution of the wave equation will take the following. Okay. The vibration of the string at any time t at any position x, okay, can be determined by the product of these two functions. Okay, you are pre-assuming that, and then you will see, okay, whether it is possible or not. That is a later case. Okay, so now means how then how will you decide now? So you have to substitute it into the differential equation. So that's the differential equation is utt equals to c square uxx. Okay, so from here you can certainly define, so utt, if you differentiate to time, f of x is equal, f of x is a function of one variable, right, x only, so there is no involving t, so you are going to differentiate 2 times g. So double dot we will denote for denote for means d square g by dt square. Okay, and uxx is going to be equal to f double dash of x g. Okay, so you have both the information. Now you can substitute these two here and see what will happen. Okay, right. So if you substitute here, so utt equals to c square uxx. So utt was f of x times d square g by dt square is equals to c square times f double dash of x, okay, g of t. Okay, right. So now f of x is, now what you can do is you have this certainly implies g double dot t by g of t is equals to c square f double dash of x divided by f of x. Now one side is a purely is a function of x and another side is function purely is a function of t. So this is only possible when both lead to the constant. This ratio will constant. Okay, So that will be certainly should be equals to some A or K, some whatever is you can take it. Okay, so these ratios will lead to the constant term. So now you have two differential equation in an ordinary differential equation now. Okay, so now let me let me see. Okay, so this is going to be lead to this. Okay, so d square f by dx square minus kf. So you take this. So here I have taken this c square here. So either way. Okay, so this you can certainly do. Okay, either ways. C square you can adjust here so that it will match with my notations. Okay, so or else you can work with here also c square, not a problem. Okay, right. So this is there. So this is the two differential equation. Okay, which you need to solve. Now this is second order linear differential equations, which you can solve by using finding the auxiliary equation, finding the particular. It's a homogeneous case only. Okay, so it's very easy to solve now. Okay, so fx f double dash of x minus k f of x is equals to 0. So instead of this a, we have considered this a. Okay, that we can replace by k. So here another correction is this one correction, and another correction is this. These are the only notation. Okay, so not worry about it. K. Okay. So you have this is equation, and you have this is minus k f of x. You know how to solve this? That d square minus k f operator notation, right? D square is nothing but d square by dx square. What is the notation for d is d square by dx square. Or what you can do is, we see this is a linear homogeneous case. So you can also look at this f of x is equals to e to the power mx. Okay, so from here, this implies f double dash of x is equals to m square e time mx. Okay, you can follow any of the process. Okay, so if you substitute these two here, what you will get is m square minus k time f of x equals to 0. So this will imply m square minus k equals to f of x is e to the power mx, right? So let me put that e to the power mx. Now you are interested in a non-zero solution, keep in mind. Okay, so m square minus k is equals to 0, e power mx will never be 0. So this implies m is equals to plus minus k root of k. Okay, now what will happen? So this is m is equals to plus minus root k, means you have this implies f of x is equals to c1 e to the power root kx plus c2 e to the power minus root kx. Now note that you have this is u at, so now you have this condition, so boundary conditions is u at 0 comma t is equals to 0 is equals to u at l comma t. Okay, now this will implies f at 0 into g of t is equals to 0 is equals to f at l times g of t. Now see, g of t can never be 0. Why? because you are interested in a non-zero solution again, right? See, u of x comma t is f of x times g of t, right? So if g of t is 0, if there is no vibration. Okay, there is no wave at any time. So that you should not, that you don't want to be the case. So g of t is never be 0. So this will lead to this condition f of 0 equals to 0 equals to f of n. So you have two conditions now for this capital F function. So now you substitute these two here. Okay. And I'm giving you, this you can say an exercise that this will lead to C1 equals to C2 equals to 0. Only 0 solution possible for this case. Okay. Why it is so? So there are various cases now. So I will start with the cases now. Case 1, I will mention here. Case 1 is, let's take k is a positive number or k is greater than 0. Okay, case 1 is k is greater than 0. So then is square root of k is possible and then everything is fine. Now case 2. Okay, let's take case 2. Case 2, k equals to 0. That also possible case. Okay, so this will imply f double dash of x equals to 0, means you have, because k time f of x is 0. Okay, k is 0. So you have, you know how, what is the solution is something like c1x plus c2. But f at 0 equals to 0, this implies c2 equals to 0. F at L equals to 0, this will imply C1 equals to 0. So this case will be implies f of x is 0 function. So that also is not considered. So this case 2 also not possible. Now case 3, let's take k is less than 0. Okay, means k is equals to some minus time a square. Okay, k is equals to minus time a square. So in that case, what you will get is another, again, the same situation, m square minus k time e to the power mx equals to 0. Now, but k is minus a square, so you have m square plus a square time e to the power mx equals to 0. So this implies m square plus a square equals to 0. This implies m equals to plus minus ai. So this will certainly imply f of x is equals to, you know, real part is 0 and imaginary part is a. So you have c1 cos ax plus c2 sin ax. Now again, you will substitute the conditions. Okay. So if you substitute the conditions now, means f at 0 is equals to 0. Okay. This will imply, if you replace x by 0, cos 0 is 1, sin 0 is 0. So C1 is 0. C1 is 0. Now f at L equals to 0. Now C1 is 0. So there is no point to consider the first term. So what you will have is, this implies C2 times sine of AL equals to 0. Now there are two possibilities. Okay, C2 is 0, then you have solution is trivial. Okay, now but C2 is not, we don't, because C2 is 0 means F is 0, means you have a no vibration. So we have already discussed all the cases. So, elsewhere it was only 0 solution possible. Okay, so since C2 is arbitrary constants, I will fix it. Let's take C2 equals to 1. This is in my hand. Okay, now C2 equals to 1. Then this sine of AL, you know, sine of x is also possibly 0, you know, right? When you have, this is argument is equals to n pi. This will, whenever n equals to plus minus 1, plus minus 2, plus minus 3, and so on. 0 also included, right? Yes. So this will give you L equals to n pi by a. or not L equals to, because L is known to you, A is unknown to you, A equals to N pi by L. Okay, so A is equals to N pi by L. So what it will give you is f of x is equals to C2 is 1, C1 is 0, sine of AX, right? So A is N pi x by L. So this is what, and since it is depending on N, I can say I have obtained the infinitely many solutions, right? And I'm not interested in the zero, so I'm not going to N equals to 0. Okay, so N equals to plus minus 1, plus minus 2, plus minus 3, and so on. These all are the solutions. Okay, infinitely many solutions you obtain. Now, if you have any question, you can ask. Okay, now if now you have A values now. Okay, K is equals to what? A is square with a negative sign. Okay, so that's equals to, that's now fixed. Okay, that's going to be minus N square pi square by N square. Now the second equation, now what is the second equation is d square g by dt square minus that k times g of t, right, is equals to 0, right? That was the equation. Minus c square k, right? So minus c square k gt. So now since k is minus a square, so this is equals to d square g by dt square plus a square c square. So you are going to have n pi c by L whole square g of t is equals to 0. Okay, now let's call this as lambda n. Okay, so I'm just going to denote it by d square g by dt square plus lambda n times g of t is equals to 0. Okay, lambda n n square you can also write. Okay, lambda n equals to n pi c pi capital N. Now again you will use a similar method to solve this. Okay, now this is all fixed, so you don't need to discuss three cases here. You are only one case here. Lambda n is positive. Okay, lambda n may be positive, may not be positive, because it depends on c. Okay, c square is positive, right? So we don't know this. Okay, now if you solve it out, okay, so this equation has 2 root plus minus lambda n I. Okay, so you have g of t is equals to c1 cos of lambda n t plus c2 sine of lambda n. So again, you have the infinitely many solutions. So far we have not used those initial conditions. U at x comma 0 is f of x, and ut at x comma 0 is z of x. Okay, so that we have not seen. So now, so therefore, what we have obtained? We have obtained infinitely many solutions un of x comma t as the product of fn of x into gn of t. So, you know, fn of x is, let's say, c1 cos of lambda and t plus c2 sine of lambda and t time fn of x was a sine of n pi x by L. So this is what the infinitely many solutions. N equals 2. You have here plus minus 1, plus minus 2. So 1, 2, 3, 4. Those are also infinitely many solutions. Now what you will do is you are going to use now superposition principle. Okay. So what you are going to use is, see, if you have finitely many solutions, you can always put the sum, and that will also lead to the solution because it's a homogeneous case. Okay. So if you look at this is equation UTT equals to C square UXX. It's a second order homogeneous equation. Okay. So superposition principle will be applied. So if you have one solution, you have another solutions, their linear combination will also follow the solution. So what you will look at is the summation of them. Okay, summation of UN. Okay, right. So we have also associated name to this U and lambda, and we are going to call them, okay, eigenfunctions, eigenvalues, okay, and so on. Okay, right. So we are going to define them as well. Okay. So I have discussed this already. Okay, so for where n is in, so we set this fine. We have done this. Okay, so this since these arbitrary constants can also be depending on n, so you C1 and C2 are replaced by Bn and Bn star. Okay, there's nothing worry about it. So the solution of the wave equation satisfying boundary conditions will be this, because so far we have not incorporate the initial conditions. Okay, that we are going to look at. Okay, so these UN are called eigenfunctions, and these lambda n are called the eigenvalues of the vibrating string. Okay, so these are the associated name, and the set of eigenvalues is known as the set spectrum. That is okay. Okay, now to obtain a solution that satisfies initial condition, we consider the following infinite series. As I told, summation n equals to 1 to infinity. This is gn of t. This is fn of x. Okay, now you have to incorporate the initial condition. Okay, so provided everything is fine, means you have this convergence of the following Fourier series or infinite series. Okay, that we will see. Okay, we are pre-assuming all the things here. Okay, so now at t equals to 0, if it's a Fourier series and it converges to this, means continuous. See this digital conditions also you can verify. Okay, those Fourier series conditions. Okay, this a function is continuous. Okay, has all the derivatives. Okay, inside the interval, piecewise continuous, maxima, minima, I mean, the number of extremum points will be finite over the interval. Okay, since it's a vibrating, it's going to be giving you the waves. Okay, so it's going to be a periodic, almost periodic, and so on. Okay, right. So those things also can be validated here. Okay, right. So we are pre-assuming that many things are in the shape. Okay, and you can assume that this actually represented by the following series. Now at t equals to 0, okay, because that theorem will says you at t equals to 0 you can obtain by replacing t equals to 0 here. Okay, so you at x comma 0 at t equals to 0, f of x implies the following. Okay, right. So see here at t equals to 0, sine 0 is 0, cos 0 is 1. Okay, so bn times sine of n pi x by n. Okay, so what is this? So this is equals to f of x. This is nothing but the sine series of f, and f is over the is interval 0 to L. Okay, so if you recall the Fourier series concept, sorry, or what you can do is you can multiply both sides by sine of n pi x by L and integrate over 0 to L. Okay, then you will see that you will obtain this bn is equals to 2 by L integration 0 to L f of x time sine of n pi x by n. Okay. In a similar fashion, what we have done yesterday was the last lecture. Okay, so this Bn is determined now. Because f is known, sine function is known, you can evaluate this integral, you can determine this Bn. Now, the second initial condition is ut. Okay, so partial derivative with respect to t and then time equals to 0. So now, if you are going to differentiate, so again, we are pre-assuming that this series is uniformly convergent and everything is nice, means you can differentiate term wise. Okay, there is no problem in that. So now if you differentiate partially with respect to t, so because this function is a function of x only, this will not alter, only these two terms will alter. So what you will obtain? Cos derivative is minus sine, so minus bn lambda n sine lambda n t, plus bn star sine derivative is cos lambda n t times lambda n. Now if you t equals to 0, this first term will get vanished because sine lambda n t will occur here. And second term will have cos lambda n t, since cos 0 is 1. So you will obtain bn star lambda n time sine of n pi x by n with some summation. Okay, right? So again, so you have the following. At t equals to 0, the partial derivative that is equal to g of x. Again, you will go with this. Okay, bn star lambda n is equals to 2 by L integration 0 to L g of x time sine of n pi x by n. Now, since lambda n, what is lambda n? Lambda n is n pi c by L. Okay, n pi c by L. So this L will get cancelled. So 2 divided by n pi c, and you will have this. Okay. So 2 divided by n pi c. So you have both the now arbitrary constants of bn and bn star are determined by using the initial condition. Okay. So with these bn and bn star, that solution will be of the wave equation. Okay. So you have bn and bn star. Okay. Now next we are going to consider the simple case. Okay. So when this velocity is 0, g of x is 0. Okay. At time t equals to 0, your initial velocity is, means you are not touching it. What will happen? Okay. What will happen is the following. So g of x is 0, means you are not having this bn star term. So this is 0. Okay. So bn star is 0. What does that mean? So bn star is 0 means this term will not occur. Only you have bn cos lambda n t times sine of n pi x by L. Now, cos lambda n t into sine n pi x. So it's kind of cos a sine b or sine a cos b, whatever. So you multiply and divide by 2. You use the formula to sine a cos b formula and simplify it. Okay. So it will take some simple shape. Okay. Okay. So from our discussion, we have bn star is 0. So solution of the wave equation takes the following form. Okay, now multiply and divide by 2 and use the fact that right, 2 sine a cos b is, use that formula, right? 2 sine a cos b is equals to sine of a plus b plus sine of a minus b. Use that fact. Okay, now so what it will lead to is, this is here. So what it will lead to is 1 by 2 bn of, bn is out. Okay, so this is 1 by 2 here multiplied. So okay, bn of sine of n pi by L x minus ct plus n pi by L x plus ct. See, here we have this replace lambda n by c n pi by L. Okay. Now, what is Bn? Bn is nothing but the Fourier series coefficient of f of x. Okay, right? So, how it will now change here is now from the fact that this represents the Fourier sine series of this summation n equals to 1 to infinity Bn sine of n pi x by L together represents the Fourier sine series of f. So, you can replace it by its, so you see, you have, if you forgotten, I may recall. So if you have f is a function, okay, f is a function defined on the interval 0 to L. Okay, so let's take, so there are two ways. Let's take, this is 0 to L, this is f of x. So there are two ways to identify its periodic extension over, because this is L, this is 0. So this is minus L. So over the interval minus L to L, if I want to observe the kind of even extension or odd extension. Okay, so there are two ways. Okay, one way is this, and another way is, okay. So if you recall, this f even extension of x is equals to, if you want, this is going to be, replace f of x, f of minus x if x lies between minus L 0 less than equals to 0, sorry, less than equals to x less than equals to 0, and f of x if 0 less than equals to x less than equals to L. Okay, so this is called the even extension. Okay, and if you want to have odd extension or periodic extension, that's going to be, replace this, you have to only extend between the minus L to 0. So you have, this is minus f of minus x if minus L less than equals to x less than equals to 0, and f of x if 0 less than equals to x less than equals to L. So can you give me in this graph which one is the odd extension, which one is the periodic extension? Yes. You can take the simple example. Okay, f of x equals to x. Okay, you can take the simple example, f of x equals to x. Okay, so x is between 0 to L is this. And between minus L to, if you want to have even extension, you are replacing x by minus x. So y equals to minus x between minus L to 0. This is going to be, right? Yeah. So this is going to be the even extension. Now, if you want to have the odd extension, so odd extension means minus of minus x. So that's going to be f of y equals to x only. So this is going to be, odd extension is going to be this. Right? So you have the following now. So this is going to see, this is going to be the odd extension. this is going to be the even extension. Okay, right. So when you have the odd extension, see, if you have the odd extension, you are getting actual the wave. Okay, that's that also you can like it. Okay, right. So here you are going to replace this by the odd extension of f with period 2l, because f is over the defined at the 0 to l. It is now f star is defined over the interval minus l to l. Okay, so this is going to be, so at when you have initial velocity, you are assuming that that is 0. You are going to have the following. Okay, this is a simple case, right? So this derived u is continuous in both variables and satisfies. So this is now you are working on the this uh, validity of this infinite series now. Okay, and also you are working on the fact that because it's whatever you have obtained, it should verify the equation c square uxx. So it satisfies the boundary condition, it satisfies the initial condition. So what is required additionally? It should be differentiable, continuous and differentiable with respect to time and with respect to x 2 times. Okay, at least second order derivatives, up to second order derivative, it is differentiable. Okay, right. So if f is twice differentiable on this, has one side, then u is the solution. So this is a very straightforward. Okay, so here, because here it is required. Okay, so on this interval, because we are going to differentiate this 2 times. Okay, so you require the differentiability of f 2 times over this interval, because we are interested in 0 to l only. Okay, and at the end point, left sided and right sided one sided derivatives are fine. Okay, sorry. Okay, so now you will say solution of wave equation. Okay, right. So we can stop here. So we can tomorrow we will look at an alternate way of solving wave equation, which is a very simple way. You will observe that you will get the similar solution in a very few steps. Okay. Okay, right. Okay, thank you. If you have any question, you can ask.